Hi guys, I hope you had a chance to read number 11 and try number 11 on page 206. If you were stuck on number 11, no worries. This is actually an introduction to the mean value theorem, which I will be introducing in this video. So this trucker drove for 2 hours and she traveled 159 miles per hour, and the speed limit that was posted on the highway was 65 miles per hour. Apparently, just based on that information, the trucker was cited for a speeding ticket because apparently she was driving over the speed limit. So think about what you can do with the hours given and the miles traveled. Like the time elapsed, which is 2 hours, and the total distance traveled is 159 miles, a total of 159 miles. I'm hoping you're thinking about the average rate of change because I am. The change in distance over the change in time. So go find her change in distance over the change in time. Grab a calculator, just think about it. 159 divided by 2. So I've done that already. The change in distance. This is her average rate. Average rate of change. This is her average speed. On average, in those 2 hours, she was going about 80 miles per hour. So here's what the mean value theorem says. It says that if her average speed was about 89 miles per hour, then her instantaneous speed at some time must have been also about 80 miles per hour. So if the average speed is 79.5, then her instantaneous speed for at least once in those 2 hours was also 79.5 miles per hour. That's what the mean value theorem says in terms of a quick application problem. Let me write the theorem, and I'm hoping you would write it with me. This is in section 5.2 for those of you who like to title the section we're covering. So we're just finishing up section 5.2 before we move on to 5.4. So the mean value theorem. Think about all the theorems we've learned so far. Intermediate value theorem was the first one. Then it was differentiability implies continuity. Then we did the extreme value theorem in this chapter. And now we're on to the mean value theorem. We've got 2 more to go before the AP exam. That abbreviation is MVT, mean value theorem, a common abbreviation. So there's 2 things about the theorem that you should be aware of. The first thing is when it works, its conditions. So if f is, I'm sure you're not surprised if I say continuous. If f is continuous on a closed interval and differentiable on an open interval. Let me grab another pen. So continuous on a closed interval and so continuous and has endpoints, closed interval, and differentiable on it doesn't need to be differentiable on the endpoints, and that's why there are open parentheses. This is the condition that must be met before you can apply the mean value theorem. So if f is continuous on a closed interval and differentiable on an open interval, then there is at least one point, we'll call that C, such that. So C in the speeding ticket and the trucker story, C is that one time or at least once that the trucker was driving at an instantaneous speed of 78 miles per hour. That's what C is. Such that the average rate of change, and again, here, the average rate of change was 78 miles per hour. We technically looked at the position, so like f of 0 minus f of 2 all over 0 minus 2, assuming that at time 0, the trucker was at home, so position 0, and then f of 2, 2 hours later, her position's 159 miles per hour, and then 2 hours went by, which will divide to give you 78. So f of b, because b is the endpoint, minus f of a divided by b minus a. This is, guys, just the average rate of change formula. Average rate of change. So, such that the average rate of change equals the instantaneous rate of change, that her average speed is going to equal her instantaneous speed. And if it's instantaneous rate of change, you know that's the derivative, and it's the derivative at c. So one more time, the trucker's average speed must equal her instantaneous speed at one time, which is sometimes c. At least once. She could have been driving 78.5. Ooh, this is the wrong paper. Sorry. She could have been driving 79.5 miles per hour more than once. But again, that's why she got the speeding ticket. So this is in section 5.2. This again is just the instantaneous rate of change, which is kind of obvious because it's the derivative rate of change. This is what the theorem says. Let's look at the theorem graphically. Can you pause the video and take out the packet that I gave in class today? So take out the packet that I gave in class today, and we're going to look at number 1. Number 1. So pause the video and get the packet. So we have a graph of x squared plus 1 shown, and the graph they want us to draw a secant line through the points -1, 2, and 2, 5. Remember, a secant line goes through the curve at 2 different points, and they want me to draw the secant line. I'll call it S for secant. It says since G, and this is the graph G being shown, is both continuous and differentiable, which, by the way, is the hypothesis of the mean value theorem. Let me just remind you, your job is to understand the portion in the purple, which are the conditions that must be met before you apply the theorem, and then we'll practice how to apply the theorem. So back to this. Since G is both continuous and differentiable, the mean value theorem guarantees the existence of a tangent line to the graph parallel to the secant line. So let me talk about where the word parallel is coming from. If they want the average rate of change to be equal to the instantaneous rate of change, average rate of change is portrayed by a secant line. So I'm going to jot that down. It's graphically, it's the secant line. And we all know instantaneous rate of change graphically, visually, is depicted by a tangent line. So if we want the secant line to equal the tangent line, it means we want the slope of the secant line to equal the slope of the tangent line, right? Because derivative, instantaneous rate of change, represents the slope of the tangent line. Average rate of change is just the boring old change of y, change of x. It's the slope of a secant line. If we want those two lines to have the same slope, we want, I should write down slope of tangent line, slope of secant line. If we want the slope to be the same, we want the lines to be parallel. That's what this question is talking about. So it says, and the mean value theorem guarantees that there's going to be a tangent line that's parallel to the secant line. Sketch such line or lines on the drawing. So here's my secant line. They just want me to draw a tangent line anywhere that I want so that it looks parallel to this line. I'm just going to eyeball it. I'm going to eyeball this sort of looks parallel. I hope it does. I'm going to call that T for tangent line. And it says lines because there could be multiple. I can only imagine drawing this one. If I draw anything on top, it's not going to be a tangent line. It ends up being a secant line. So I'm going to recap, and I'm sorry if I'm talking too much. I know it's already 9 minutes of the video, but I'm trying to hurry. This is the average rate of change. This is, in the trucker situation, her average speed. This is her instantaneous speed. The mean value theorem says if her average speed was close to 80 miles per hour, then I guarantee there was at least once that her instantaneous speed was 80 miles per hour. The derivative is representing the instantaneous rate of change. This formula represents average rate of change or average speed. Graphically, this is just change of y over change of x. It's a slope of a boring old line. It's a slope that has 2 points, and it's a slope of the secant line. Graphically, this represents the slope of a tangent line, and that's what a derivative represents. If we want them to be equal, if we want their slopes to be equal, then those two lines are going to be parallel. So this represents, the slope of this line represents average rate of change. The slope of this line represents instantaneous rate of change. I found, it seems like somewhere here, I found one special C. I found one special C, and here's what's so special about this C. The derivative at C, which is represented by the slope of this tangent line, is equal to the slope of the secant line, which is the average rate of change. Part C says use your sketch to visually estimate the x-coordinate. Somewhere here, I'm going to say between 0 and 1. Yeah, that's where I would estimate it. You don't have to estimate the same place. Maybe my line doesn't look very parallel. Maybe you used a ruler, your line came out to be better. D says that x-coordinate at the point of tangency is the value of C promised by the mean value theorem. Verify your answer to part C by using the conclusion of the mean value theorem on the interval. So here's me applying the theorem for you. And again, they want me to verify my answer to part C. Like, this was just an estimate, this special C value. They want me to actually verify it. So the mean value theorem wants me to find, first it wants me to find average rate of change. Let's do that. Average rate of change between these 2 points. So I'm looking at the average rate of change between -1, 2 and 2, 5. And I'm just going to do the boring old slope formula. 5 minus 2 over 2 minus -1. And that gives me 1 after I've reduced. They want me to put this 1 equal to the derivative at C. My job, guys and girls, is to find C. Again, I'm trying to find this x-coordinate. So I'm going to put the derivative. Here's my work, actually. Here's the average rate of change. I'm going to put it equal to the derivative. Let me take this away, sort of. And then the derivative, if this is just a function, it's x squared. That's what g is. The derivative of that is just 2x. I called it 2c because I'm solving for c. And then 2c equals 1, that means c equals 1/2. This point, that's actually a pretty decent approximation. This point is 1/2. So this is me applying the theorem. This is what the theorem looks like graphically. All right, let's look at number 2. Number 2 says determine whether the mean value theorem applies to this function on that closed interval. And if it applies, find all the values of C guaranteed by the theorem. Now, remind yourself of the hypothesis. My function must be differentiable. It must be continuous on a closed interval and differentiable on this open interval, meaning that it's okay if it's not differentiable at -2. The mean value theorem is still going to work. It's okay if it's not differentiable on 3. Actually, my dilemma is here. If you look at this function is discontinuous at 0. It's discontinuous at 0. Even if I reduce it, it reduces to 1 plus 1 over x. It's discontinuous at 0. And if it's discontinuous, you know it's not differentiable. So f is discontinuous, so the mean value theorem cannot be applied. That's it. We're not applying it because that's what it said. I want to do one last one, not number 3. If you turn the page, I want us to do number 5 on page 2. Let's look at number 5. Last one, I promise. Last one. So there's a g is differentiable. Remember, if it's differentiable, it's also continuous. Jot yourself a note. Also continuous. And now the table shows values of g and g prime. Is there a number c in the closed interval from -5 to -3 such that the derivative equals -4? So can you find an x value where the derivative equals -4? Now, before I apply the mean value theorem, let's make sure it's applicable. This function g is differentiable, and if it's differentiable, it's also continuous. So big thumbs up. I'm trying to draw a thumbs up. Big thumbs up to the mean value theorem. And you should address that. We should address it. That since g is differentiable, then it's also continuous, allowing us to use MVT. Let's go use it. Let's go answer the question. Is there such a number C? So they want my derivative to be -4. So the derivative needs to be -4. Let's confirm that. Let's see if the average rate of change in this interval is -4. I'm only stuck from -5 to -3. That's the interval I'm supposed to look at. I'm finding average rate of change. Again, right, if this was f prime notation, when you do average rate of change, you do f of b minus f of a. You don't do f prime of b. You do f of b minus f of a. I'm trying to convince you that this is extra information. I don't need to use the values of the derivative. I need to do g of 10. I'm going to do g of -5 minus g of -3 divided by -5 minus -3. G of -5 is 10 minus g of -3, which is 2, divided by -2, and look, OMG, it equals -4. The average rate of change equals -4. Is there a number C in the closed interval such that the instantaneous rate of change is going to equal -4? There sure is, because the average rate of change equals -4. So yes, there will be a time where the instantaneous rate of change will equal -4. For example, the trucker situation. Let's imagine her average rate of change was -4 over, let's say, the 2 hours. Then it is the case where her instantaneous rate of change at some given time will be -4. And then that's the answer. Okay, thank you for watching.